Hello everyone, welcome back. Today's video is on groundwater chemical transport. The learning outcomes of today's video is to define chemical retardation, and then we're going to evaluate Darcy's law with questions involving chemical retardation as well. So as we know now, groundwater flows, and the speed and velocity at which that flow occurs is governed by Darcy's law. And that is a proper ratio. It's a function of the change in elevation of our water table multiplied by the hydraulic conductivity, that K value, which is a property of our sediment. Water can carry lots of chemicals with it, and so groundwater is no different. When things spill into the earth, they are soaked up like a sponge and then transported once they enter the water table here. So you can see you have your spill site next to a property. Maybe it is a leaking gas can, a buried gas cylinder. Maybe it's an overtoppled vehicle. That spill site will spill into the earth, and then once it hits the water table, it'll start diffusing out into the groundwater of the water table and be transported at a rate that we can predict. And if you can know the way that this chemical interacts with our sediment, lots of chemicals have different functional groups that are going to interact with sediment differently than other chemicals. Some of them are going to be more insoluble in water and not be transported with the plume. Some of them are going to bond really readily with sediment, and some of them less so. A chemical that doesn't bond with sediment is going to be transported at a rate more similar to the groundwater flow than one that doesn't. So one that bonds a lot to the sediment is going to be transported much slower than the groundwater surrounding it. If you can predict the behavior of groundwater contamination, you can treat it effectively. And so the big way that we treat groundwater contamination is called a pump and treat. And so you basically drill a well into your spill site, or you use another well in another area, and then you start sucking out groundwater from that well and eventually remove the contamination from that. You treat that water with some water treatment system, and then you inject that back into the ground. And so it's a very active process. You're removing the water from the sediment, and then you're returning the clean water to the sediment. So removing the chemical and intercepting it in some water treatment process in the meantime. So this is really important and a very important question that people need to answer. And so chemical retardation is a scientific term. Being retarded means you're slowed in some way. And so chemicals bond with soil slightly, and that slows down the flow of that chemical. And so that's represented by the R value, which is our chemical retardation coefficient. And this is a ratio of the distance that that chemical travels in an environment compared to that distance traveled if it was not being affected by these chemical factors, if it was moving through an inert, unsorbed environment. Sorption is something that scientists use to refer to adhering to something. Adsorption and absorption are different chemical processes at play. And so if you don't know which chemical process is happening, you can just call it sorption as a generic term. So you have sorption, and then you have adsorption and absorption that make up that sort of blanket term sorption. So that's what SORB means, sorb. It's just adhering in some way. The chemical is binding with the sediment somehow. And so our R value captures that slowness that is experienced by a chemical with a lot of chemical bonding. So here we have just a piece of paper that's been stuck into some water, and it has 4 different dyes attached to it, all that have been retarded at different speeds. So we can assume these have all been in there at the same time. And so over that same time, the red dye was able to travel a lot farther. And this line at the very top is our water. So it was almost able to travel as fast as that water moved. So it was not bound to the paper in any way. It wasn't held back. It wasn't retarded. And so this is going to have a low chemical retardation coefficient. Whereas the yellow one here is interacting with the paper a lot, so much so that it's been inhibited quite a bit. In the same distance it took this red dot to travel up that distance, this yellow dot did not travel very far. And all of this is traveling by capillary action. This is actually something you can do at your house with various food dyes because they all have different actual chemical dyes in them. And so each of those chemical dyes will move up the paper at a different rate. And so you can measure this in situ by looking at concentration diagrams and figuring out this value based off of that, or looking to the literature to see how this known chemical, hopefully known chemical that's been studied, interacts in the environment. And so Darcy's law and chemical retardation can come and play into each other to allow us to calculate the velocity of that chemical, the velocity that that packet of chemical is moving at. And so that is the velocity of this red dot here is moving at some speed. And so we want to know that. And so with chemical retardation, now the speed of the chemical is not the same as the speed of the water. So our velocity of our water divided by R equals the velocity of our chemical. And R is usually a value that's greater than 1. And so when you divide by a number greater than 1, your velocity is going to decrease. And in terms of Darcy's law, that is negative Ki, our hydraulic gradient, dH, dL, divided by R. So we're slowing the velocity at which this chemical moves at. And so before we move any further, before we wrap up today, we're going to do an example. So using Darcy's law, let's find the velocity of the groundwater in the well below. And then we're going to find the velocity of the chemical contaminant given that the chemical retardation is 21. And so we have our water table. There's 2 wells here. One is measuring a height of 50 centimeters, while the other one is measuring a height of 30 centimeters. So our H1 here, let's see if I can get the right pen. Our H1 here is equal to 50, and our H2 is equal to 30. Now, in these questions, sometimes you can be given a value X over here, where this is 0 at our datum at this area, and then 50 centimeters over here. But this question has actually just provided us the length. And so this is our DL is 50 centimeters. And so H1 minus H2 equals equals 20 centimeters. So our DH equals 20 centimeters. And remember, we're solving for Darcy's law, which is V equals negative Ki negative Ki. And so we're going to find the velocity of the water first before we move any faster or proceed to look into the chemical retardation. And so I, remember, is equivalent to dH dL. And so our dL equals 50. So that means our dH dL is 2/5. 2/5, which is 0.4. 0.4. And so plugging this into here, we aren't really interested in which direction this is moving in, but we know that it's moving from left to right because things like to move downhill, and we sort of have a hill of water moving downwards to the right. So it's going to flow from left to right. Our K value is 10 to the -5 centimeters per second. And so we simply multiply 0.4 times 10 times 10 to the -5 centimeters per second. And remember, this is unitless. Make sure that you are working with the same unit on top and bottom, the same length on top and bottom. This can be centimeters, this can be meters, because by the time we calculate DHDL or our I value, our hydraulic gradient, it has no units. So this is just 0.4. And so multiply those together, 10 to the -8/5, 10 to the -5 times 0.4 is equivalent to 4 times 10 to the -6. 4 times 10 to the -6 centimeters per second, which feels like a slow velocity, and it probably is, but groundwater flows are concerned with really long time scales, months, years. And so this is the velocity of our water. Now, our velocity of our chemical, we need to include this chemical retardation, our R value. And so it's equal to the velocity of our water divided by R. And so it'll be 4 times 10 to the -6 divided by 21. Divided by 21. And let's see what that gets us. Okay. 1 times 4 divided by 21. So my answer I got was 1.9 times 10 to the -5th. That is not adding up. Let's see. So, oh, I know what I did wrong. Okay, times 4 divided by 21. I got 1.9 times 10 to the -7th. 10 to the -7th centimeters per second. So the chemical is moving a lot slower than our water. And over time, if we keep contaminating our groundwater, it's actually going to concentrate the amount of contaminant that's in the groundwater because our water is proceeding faster than that chemical. And so if you keep pumping in more water that's contaminated, the soil is going to act as kind of a filter and intercept more of that chemical and increase the concentration that is felt by that soil. And so that can have pretty dramatic impacts on the environment. that concludes our video for today. Feel free to reach out to me if you have any questions. Thank you.